Good morning, students. Let's see the continuity of oxidation states in transition elements. Okay. So before going to discuss about this, just write two important catalysts and their names. CO2 taken 8, carbon monoxide, cobalt. So name of this catalyst is dicobalt, dicobalt octacarbonyl. Name of the compound, it is the catalyst, we call it is hydroformyl catalyst or oxo process, we call it is hydroformyl catalyst. It is the catalyst dicobalt octacarbonyl. It is the catalyst. So why we use this? Alkenes converted to aldehydes, aldehydes, alkenes converted to aldehyde, and Bordeaux catalyst. So what is the composition of Bordeaux catalyst here? That is calcium sulfate and calcium hydroxide. I think already we discussed about this Bordeaux catalyst and use of Bordeaux catalyst. Already discussed about this. It is used as fungicide. Remember this, fungicide. Okay. So these are the two catalysts. Note it down. Fungicide used as Bordeaux catalyst, already discussed about this. This one is new catalyst here. And let's see the continuity of D block oxidation states part 2. So in this, in the case of non-transition elements, that is P block elements, P block elements, heavier elements heavier atoms of elements have low oxidation states, low oxidation states state is stable. In the case of heavier atoms of elements have lower oxidation state, that lower oxidation state is more stable in the case of non-transition elements. For example, thallium, it is P block elements, 13th group element in the periodic table. Thallium, its valence electronic configuration is ns2 np1 ns2 Ns to Np1. This is the valence cell electronic configuration of thallium, outermost cell electronic configuration. There are 3 electrons are there. One is p, another one is 2. But these 2 electrons which are in S not willing to participate in chemical reaction. So Ns2 electrons not willing to participate in chemical bond. That phenomena is called as inert pair effect. Already we discussed about that in the first year. Inert pair effect. These Ns electrons unable to participate in the chemical reaction. That phenomena is called as inert pair effect. Inert means chemically not willing to react. Remember this. And now actually these 3 electrons need to participate in the chemical reaction, but in the 13th group we have boron, aluminium, gallium, indium and thallium. These are the 13th group elements. So in here it is exhibit maximum +3 and +3. Here also it is +3. From here up to it is +3 and +1. Here it is mostly +1 it is exhibit. Okay, mostly it exhibit +3 oxidation. Mostly +3 oxidation state here. But in the case of thallium, it exhibit only +1 oxidation state. Why? What is the reason? In case of 13th group elements, the general electronic configuration Ns2 Np1 for all these boron family. So number of valence electrons in the 13th group elements 3 only. But up to here, these 3 electrons participate in the chemical reaction. But in the case of thallium, so these p electron only participate in the chemical reaction. So thallium can easily lose only 1 electron only, which is present in Np, not these 2 electrons which are present in Ns. Clear? So in the case of thallium, this is heavy atom, heavier elements. The last one, heavier elements, these are which are present at bottom of the group. Okay, so generally these can able to lose these 3 electrons, 2 electrons from S and 1 electron from. But in the case of thallium, what happened? These electrons are not willing to participate in the chemical reaction. So that effect is called as inert pair. So which electron participate now? Only this electron which is present in P only able to participate. So thallium can exhibit as +1. Thallium +1 only. Thallium +1. That is the stable oxidation state. Stable oxidation state. So one is very less, right? So very lower oxidation state. That lower oxidation state is stable in the case of heavier elements in P block non-transition elements. Okay? Is it clear, students? In the case of non-transition elements, heavier elements process lower oxidation state. Why? Because inert pair effect. Lower oxidation state is the stable oxidation state in this case. Okay, clear? Now, but in the case of transition elements, transition elements have that elements are heavier elements. Which are present bottom of the group. Heavier elements, in the case of transition elements, heavier elements have high oxidation is stable oxidation state. Stable oxidation state. Higher oxidation state is stable in the case of transition heavier elements. But in the case of 13th group, +1 is the most stable oxidation state. Why? Because Ns electrons unwilling to participate in the chemical bond. But in the case of transition elements, higher oxidation state is the most stable oxidation state. Let's see the example regarding this. So what is that? For example, if you take 6th group sixth group of transition elements or sixth B. Then we have chromium. Okay, chromium and molybdenum, tungsten. Here chromium exhibit +6 and here MO molybdenum is also exhibit +6 oxidation state, and here also molybdenum and tungsten it exhibit +6, all are +6. This is in sixth group, but here these are heavier elements. These two are heavier elements. Now, which one is stable oxidation state here? This chromium 6 is light element, and molybdenum is 6, and tungsten is also exhibit 6 oxidation state. Now these two are stable oxidation state. Stable oxidation state. In the case of heavier elements, maximum oxidation state is stable. That what is the oxidation state here? +6. But in the case of non-transition element, lower oxidation state is more stable. In the case of heavier element, thallium is heavier element, it shows +1 oxidation state. That is low oxidation state is stable. But in the case of transition elements, heavier oxidation state is more stable. That is the difference. Okay. So let's see. That means here chromium 6 is reactive. That means less stable comparing with these two. Okay. MO and tungsten 6 are stable. Okay. Stable. Why? Because these are heavier elements. W means tungsten, wolfram qualities. Okay. So let's take the compound K2Cr2O7. Chromium is there. Potassium dichromate. In presence of H2SO4 sulfuric acid, which is called acid, act as strong oxidizing agent. Strong oxidizing agent means it helps to oxidation by itself undergoes reduction. It helps to, this is K2Cr2O7 potassium dichromate. This is another. This K2Cr2 will offer 2 electrons to this compound. Then it gains the electron. This one undergoes reduction. That means oxidation. Strong oxidizing agent means it helps to oxidation means K2Cr2O7 attract the electron from other. Now it is lose the electron. Then that means it undergoes oxidation. Okay, so it gains the electron, that means it undergoes reduction. Loss of electron is called as oxidation, gain of electron is called as reduction. Now K2Cr2O7 gain the electron from this compound, then it undergoes oxidation, then it undergoes reduction. So now K2Cr2O7 potassium dichromate is strong oxidizing agent in presence of H2SO4. Acidic medium. We prefer mostly concentration H2SO4. Remember this. Okay. It is reactive in this case. It is reactive. Let's calculate the oxidation state of chromium here. How many chromium atoms here? We have 2. So take as 2x. Would like to calculate the oxidation state of chromium in this compound. Here chromium we have 2x. 2 chromium atoms 2x, and potassium we have 2. Each potassium carries +1 charge, and oxygen carries 7 oxygen atoms. each oxygen carries -2, then total equals 0. Okay, then 2x plus 2 minus 14 is equals 0. 2x minus 12 is equals 0. 2x is equals to plus 12. X equals to plus 6. Now what is the oxidation state of chromium? Plus 6. Okay, therefore oxidation state of chromium in K2Cr2O7 potassium dichromate is plus 6. Plus 6 or not? Already we discussed plus 6. But in potassium dichromate it's very reactive. Act as oxidizing agent. Oxidizing agent means it helps to oxidation to others. That means it gains the electron from other, then other compound lose the electron. Loss of electron means oxidation. It gains the electron. This compound is gain the electron. This compound. Then that means it undergoes reduction. Oxidizing agent itself, it helps to oxidation by itself undergoes reduction. Clear? Remember this. So now come to these two compounds MOO3 and WO3 and calculate oxidation state of this one. How many molybdenum here we have? 1. So taken as X plus how many oxygens? 3. Oxygen carries -2 charge. Keep 2 here. Why? Because we have 3 oxygen atoms. Totally equals 0. X minus 6 equals 0. X equals plus 6. What is the oxidation state of molybdenum here? Plus 6. Calculate here. And X plus 3 minus 2 is equals to 0. Clear ma? Up to. Then X is equals to plus 6. Am I right? Plus 6. So now, but these two are heavier elements in 6th group. Am I right? In the case of transition elements, heavier atoms shows maximum oxidation state. That oxidation state is stable oxidation state. Here chromium is less stable oxidation state, even though it is 6 oxidation state, but it is less, it is lighter element here. Remember this. It is heavier elements. More molecular mass weight is there in this case. So plus 6 is stable in the case of, but in non-transition elements, thallium is heavier elements, even though it is less oxidation state, that is the stable oxidation state. Remember this. Thallium shows +1 oxidation, that is the stable oxidation state. Okay, remember. Okay. In the case of heavier transition elements, maximum oxidation states of heavier elements is stable oxidation state. Example, molybdenum and tungsten. In the case of non-transition elements, example 13th group element where thallium is clearly heavy elements. In that case, +1 is very least oxidation state when comparing with transition elements. Okay, so that is stable oxidation state. That is the difference. So copper and chromium shows least oxidation states also, that is +1. Both are exhibit. Copper can exhibit +1 and chromium can also exhibit +1 also. That is the least oxidation states in the transition elements. Okay, and some of the stable oxidation states in transition element, stable oxidation states, you just remember it is stable oxidation states. So copper it exhibit +1 also. Cobalt silver it exhibit +1. Mercury also exhibit +1. Okay, tungsten is also exhibit +1. Molybdenum is also +1. Okay, these are the some of the important stable oxidation state, and very stable oxidation states also we have. Very stable oxidation states, very stable oxidation states. For silver it is +1, and platinum, palladium both are exhibit +2 and also +4. +2 and +4 also exhibited by platinum and palladium. Mercury can exhibit +1 also and also +2. Is most stable oxidation states for this. Okay, and the tungsten is also +1. Okay, and let's see. Scandium most stable oxidation state +3 only. Remember this, it does not show variable oxidation state. Scandium does not show variable oxidation states. Variable means +2, +3, +4, +5, +6, and that different types of electronic configuration does not show like that. It is shows maximum +3 only. So scandium does not show variable oxidation states. Remember this, and the same pattern zinc also does not show. Zinc and also cadmium, okay, does not show variable oxidation states like scandium. Okay, zinc always shows +2 and cadmium is also +2 only. They does not show variable oxidation states. Why? Because if we consider zinc that electronic configuration is argon 4s2 3d10. Zn plus 2 means remove these two electrons, then it become argon 4s0 3d10 3d10. Okay, so in the case of Zn plus 2 it gets 3d10. This is fulfilled d orbitals we have, am I right? Fulfilled d orbital is more stable, then it is unable to lose the electron. So Zn plus 2 is stable oxidation state for zinc. So it is shows maximum Zn plus 2 only. So it does not show Zn plus 3, Zn plus 5 like that. Okay, so it does not show variable oxidation state. Okay, and same in the cadmium also belongs to same group. Okay, same group, second big group. It is also like that, 4d10. Okay, cadmium in the outermost cell it is 5s2 4d10. It is also after losing of 2 electron in the d orbital it also processes 10 electrons, get stable, more stable. Okay, remember this. These are does not show variable oxidation states. Okay. 3D transition series. Okay, so 3D transition series starts from scandium to zinc. Am I right? Okay, scandium. What is its stable oxidation state? +3 only. After scandium we have titanium. Am I right? These titanium can show +2 oxidation state, +3 and +4 also. +4. So here +2 +4, and vanadium it exhibit +2 +3 +4 +5 oxidation states, variable oxidation state, but it does not show variable oxidation states, only +3. But titanium shows +2 +3 +4 also. That is variability here. Remember this. Okay, variable oxidation states are possible here, but in this case it shows only +3. Okay. Then chromium, so it shows +1 oxidation states, +1, so minimum oxidation state +1, and +2 +3 +4 +5 and +6. Here +4 and +5 is unstable, not stable oxidation state. unstable, unstable oxidation states. Okay, manganese, manganese plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. Okay, maximum oxidation state plus 7. Okay, this plus 5 is unstable. Plus 5 is unstable. What is the maximum oxidation in the 3D transition series means? Plus 7 is the maximum oxidation state, that is manganese in 3D transition series. It belongs to 3D transition series, that shows maximum oxidation state. Okay, and iron it shows plus 2 plus 3 plus 4 plus 6 plus 6. These two are unstable oxidation states for iron. Okay, that means these two are stable oxidation states. Okay, clear? That is cobalt plus 2 plus 3 plus 4, this is unstable, and nickel also plus 2 plus 3 plus 4, and copper it exhibit plus 1 plus 2, and zinc that is only plus 2. Okay, for copper mostly both are stable oxidation states. For iron plus 3 is most stable oxidation state. Okay, is it clear, ma? Here zinc is not so variable oxidation state like scandium. Okay, remember this, already told that. So which is in parenthesis, that means in this bracket those are unstable oxidation states, remember this. So here stable oxidation states for titanium, most stable oxidation, these are all stable, but most stable oxidation for titanium is and plus 4 oxidation state is most stable. For vanadium most stable oxidation state is plus 5, and chromium it is plus 3 and 6 oxidation state is more stable for chromium. For manganese it is, for manganese Mn plus 2 is more stable oxidation state for manganese. What is the maximum oxidation state? Plus 7. Keep this manganese shows maximum oxidation states in 3D transition series. Okay, and after manganese, iron it shows plus 3 is more stable oxidation state. Okay, and cobalt, that is plus 3 is more stable oxidation state for cobalt. Okay, and what about nickel? Nickel shows more stable oxidation state plus 2, and copper it is plus 1 and also plus 3 is more stable, zinc plus 2. Okay, clear? These are the most stable oxidation states in this. Okay, so which are in parentheses in this bracket, this is unstable oxidation states. Okay, keep this in our mind. So simple, scandium does not show variable oxidation state, zinc does not show variable oxidation state, cadmium does not show variable oxidation states. Remember this. So in 3D transition series, which one shows maximum oxidation number? Manganese plus 7. Okay, remember this. And come to now seventh group, or seventh B group also. Seventh B group also. So in the seventh B group, we have manganese and technetium and rhenium. These are the elements, the rhenium. This belongs to 3D transition, this belongs to 4D, and this belongs to 5D. Okay, these all are source maximum oxidation state plus 7. Why? Because these are belongs to same group, 7th. Manganese in 3D series, which one is the maximum oxidation state? Manganese. and 4D transition series which one shows maximum oxidation state, that is +7 technetium, and in 5D series which one shows maximum oxidation state, rhenium, that is +7. These three are belongs to 7th big group and shows maximum oxidation states, remember this. And come to eighth group which are related to eighth group. Okay, so here in this case, if you object iron, and after this ruthenium and osmium, So here iron maximum oxidation state +6 it exhibit, but stable oxidation state is +3 in the stable oxidation state. Okay, this is 3D and this is 4D, this is 5D. You should have to remember this also. Ruthenium belongs to 4D transition, osmium belongs to 5D. Okay, so in the 4D series, the maximum oxidation state is shown by ruthenium, that is +8, and also osmium +8. Very important. Entire periodic table, these two are shows maximum oxidation state. Not only in this 4D transition, ruthenium shows +8 and osmium +8. Okay. Now what are the compounds? Ruthenium tetraoxide, okay, and osmium tetraoxide. In this compound, suppose I have to calculate oxidation state of ruthenium. So ruthenium 1 is here, that is taken as X, and how many oxygen? 4. Each oxygen atoms carries -2, is equals to 0. Then what is the value of X? Equals +8. So what is the oxidation state of ruthenium? +8. Same osmium also +8. Okay. So where ruthenium exhibit +8 in this compound. Okay. Osmium also plus. But osmium tetraoxide, which is shows +8 oxidation state, is more stable. Here. But +8 in this case it is less stable. It shows maximum oxidation state +8, but in case of ruthenium tetraoxide it is less stable, but osmium tetraoxide it is more stable, +8. Both are exhibit +8, that is the maximum oxidation state. One is belongs to 4D, another one is 5D. Is it clear, my students? Up to? Okay. So very important this. In the case of 7th B, manganese +7 and also technetium +7 and rhenium +7. 3D, 4D, 5D. In the case of 8th B, ruthenium exhibit +8, that is the maximum oxidation state, and osmium also. The compounds are ruthenium tetroxide and osmium tetroxide. Okay, but in this case, this molecule is more stable by it exhibit +8, but even though it exhibit +8 is unstable. Okay, remember this. So +8 is unstable in the case of ruthenium. Remember this. Okay. Scandium, zinc, cadmium does not show variable oxidation state. Why? Because they are stable. Zinc +2, cadmium +2, scandium +3. Okay, students, again we'll meet on tomorrow. Have a nice day. Thank you very much.